honor to introduce Daniel Limonadi, a fellow Californian. Daniel is the Chief System Engineer for the Earth Science and Technology Directorate at Johnson Propulsion Laboratory, where he is responsible for supporting activities ranging from technology and new process development to flight project formulation and implementation through providing advice on strategic direction. He has been at JPL since 1999 and has held systems engineering leadership positions on several Earth science flight projects and research and development tasks, including the Curiosity Rover project and the Mars Exploration Rover project. Before coming to JPL, Daniel worked at Hughes Space and Communications on the development of the HS-702 spacecraft product line. He received his Bachelor of Science degree in aerospace engineering from the University of California at Los Angeles and enjoys taking continuing education classes and studying engineering and Earth System Science. He has received 2 NASA Exceptional Achievement Medals. The EAM is awarded to any person in the federal service for specific accomplishment or substantial improvement in operations, efficiency, service, financial savings, science, or technology which contribute to the mission of NASA. As I read about the EAM awards, the key words that stood out were high quality, substantial improvement, innovative approach, impact, and importance to the agency's mission and goals. I am now honored to welcome Daniel Limonadi.
Thank you so much for giving me the opportunity to talk to your group today. Really, really appreciate it. And this is a fun topic. It's kind of cool to engage in, so I'm going to share my screen here. Kind of as implied by the reading, right? We're going to talk about big topics today, thoughts on life in the universe. This is, I think I only have 20 minutes, right? So it's going to be a very short version. The pale blue dot video and reading that you heard from Carl Sagan was referencing this image, which was taken by the Voyager 1 spacecraft back in 1990, looking back at Earth, and that little dot, right, a couple of pixels of light, when Voyager 1 was past the orbit of Neptune, is the kind of what inspired that pale blue dot, right? So the point was to give us a little perspective, which I think we all need these days, right, when people are making a lot of hullabaloo about things that maybe aren't so important in the grand scheme of things. But anyway, we're going to talk about life in the universe and the kind of cool thoughts that come with that. So one of the things we need to think about is how long, how big is the universe and how old is it? Because that influences, a lot of things we think about as far as likelihood of life. So this picture that you're looking at, each piece of light in this picture in the background that I'm sharing, that's a galaxy, right? This is the Hubble Deep Field image that was taken about 20 years ago now. And where Hubble just kind of stared at what was kind of an empty black part of space, where even a lot of our telescopes couldn't see things, couldn't see a lot of stars. And it's just a great reminder of how big everything is, right? If you look at the objects here, again, everything you're seeing here is a galaxy with probably 100 billion plus stars, right? And so again, it's just kind of a humbling view of what we have. And so I'm going to go through this pretty quickly, right? When you guys were younger, we thought the universe was pretty small, maybe only a few thousand light years. But the bottom line now is, the universe's size is kind of limited by how old we think it is. We think the universe is about 13.8 billion years old, and because of the speed of light, when we have estimates of the size of the universe, it's just limited by how long the light can come to us. So, we think there's hundreds and hundreds of billions of galaxies out there, but again, it's limited by the light that can make it to us, given the age of the universe. And by the way, one of the fun things about astronomy is things are always changing. With the launch of James Webb Space Telescope and some other observations we're making, this age of the universe estimate that we've had of about 13.8 billion years that Hubble Space Telescope came up with is now being challenged, and now we think maybe it's twice as old. So there's just a lot of stuff that's going on. Like we need to stay humble in this field, right? We don't really know a lot. Real quick, I'm not going to go into the details here, but basically there's science and things that we look at to figure out how far away things are, how old the universe is, etc. We can skip the details given the time that we have. But the bottom line, right, is there's a lot of stars. And I think when you guys were younger, when I was a kid, we didn't even know if there were any planets besides the planets around our star, the sun. Since that time, especially starting in the 2000s, we've launched spacecraft that specifically look for planets around other stars. And now we know statistically each star has at least one planet on average, if not many more. So our sun indeed is just an average solar system in the universe as far as we can tell. So what does that mean as far as quantity of things, right? So a good thing to kind of imagine, I think hopefully you guys have all been to the beach before, right? You're in Virginia on the coast, or at least close to the coast. If you pick up a handful of sand, there are thousands of grains of sand in that hand. Okay, so now imagine all the beaches of the world and all the grains of sand in all the beaches of the world. There are more stars in the universe than there are grains of sand on all the beaches of the world. Okay, so that's a little bit humbling, right? It's a big number, right? So there's hundreds of billions of galaxies. Each galaxy has hundreds of billions of stars. Each of those stars on average has at least one planet. So there's 10 to the 22, right? A 1 with 22 zeros behind it. Planets, stars and planets in the universe, right? It's a giant number. And so an obvious question is like, well, hey, life seems to be pretty prolific on this planet. If we imagine that there is life on other places, even if it's very rare, when you multiply very rare by 10 to the 22, you still get a lot, right? And so a question we ask ourselves is, where is everybody, right? So we're going to talk about that. So kind of part of jumping into that, right? We need to think about what do we know about life as we know it and maybe as we don't know it. And of course, this is a picture of life on Earth. And as we know, Earth flaunts its life, right? If you're looking at Earth from space, it's pretty obvious we have life here. So I don't know if you've probably heard of Stephen Hawking. He's a very famous astronomer, cosmologist, and he came up with a pretty general definition of life, which is just, something, an ordered system that can sustain itself against the universe's tendency to disorder. There's actually a second law of thermodynamics that says, in the big picture, the universe kind of wants to go to chaos, right? Entropy, increased entropy. But their life is kind of a little resistance to that, basically, that this tendency of parts of the universe to create order, even though the bigger universe wants to go to disorder, and that thing can reproduce itself. That's the most generic definition. And then a living system usually has two elements, some instructions on how to sustain and reproduce itself, and then some mechanisms to carry that out, right? That's the most generic thing. For life, for biological life, the stuff that just springs up from natural elements in the universe. What does that mean? You need compatible chemistry. So for on Earth, that's carbon-based stuff and water. You need energy sources, right? Aerobic, either anaerobic. So it turns out there's tons of options for energy that are not aerobic. So methane, sulfur compounds, hydrogen, ammonia, ferrous iron, basically anything chemically that provides energy. If you add some water, life can make a living there. Photosynthesis is kind of an obvious thing that we think about on the surface of the planet, right? And then aerobic life for the things, like animals that eat stuff. We can use sugars and oxygen to create a lot of energy. So we need an energy source. We need maybe a lot of time, right? On Earth, we think it maybe took tens of millions or a few 100 million years for single cell life to form. And then after that, about 3.5 billion years for multi-cell life to form. So time is kind of important for chemistry to just experiment and figure out to organize itself. You need temperature and you need some stressors, right? For life to get interesting and have a lot of diversity, you need stuff to stress the life out. Extinction events, environmental change, those things drive evolutionary creativity long term. So on Earth, that's created everything we know, right? Everything from single cell bacteria to us, crazy advanced monkeys, right? So One of the other things that's changed since we were younger, right? Since maybe most of you guys were in school, I was in school. I was taught when I was in school, and I'm 50 something, that life is very sensitive. Everything has to be just perfect. There was this kind of like Goldilocks theory of life. And over the last 50 years, we've learned that is completely not true, right? And if you remember the quote from the movie Jurassic Park, life finds a way. That's kind of what we discovered. And so on Earth, everywhere we look, like literally everywhere, the deepest hole that we've dug, like 5 mile deep, you know, um, drill wells or mines, if there is a little bit of water around, we see single cell life kind of all over the place. So life has completely covered the surface and subsurface of our planet. I talked about this living underground. We have life. There's bacteria living inside nuclear reactors, right? I'm going to show you an example. So there's single cell life that has triply redundant DNA, and it can fix its DNA faster than the radiation from the nuclear reactor can destroy it. So again, life is not a Goldilocks. It is tough, and it's really hard to kill. It can also be dormant for tens of thousands, sometimes even maybe millions of years, and then can wake up, like add some water, make the conditions right, and the bacteria can go from spore form back to normal form, right? So another example of it being really tough, it's gone to space, it's come back, right? So here's some example. This is a lower left hand is kind of a bacteria that's called Conam bacterium. It lives inside nuclear reactors and is very radiation tolerant. Other examples of single cell life, and then this is the tardigrade, water bears, I think they're called, right? That's multi-cell life that also can live in space and do other stuff, and survive. So anyway, the universe is really old. It's been around a long time, and life is really tough. And so, it seems like we would expect it to be maybe in many places. In our solar system, one of the things we think about is, where could there be life in our solar system besides the Earth? And, places that we will be looking in the future, there are places in the gassy planets. So both like Jupiter, Saturn, they have water kind of at the liquid point at places in their atmosphere. Even though they're giant planets, there are places in their upper atmosphere where we think liquid and gaseous water can exist together. And we see clouds and things like that. Same thing with Venus. Even though Venus is super hot at the surface, that's the planet on the right, we think in the upper atmosphere of Venus, there's actually liquid water. And, we see living things in the clouds of Earth. And, there might be life in those places. We don't know yet. We haven't found anything obvious yet, but we're going to look a little bit harder in the future. Obviously, ocean worlds. So there are moons in our solar system. Europa is shown here in the lower left-hand corner. I could spend an hour talking just about this moon, but I don't have time. It's a icy moon with an ice shell and then an ocean that is bigger. It has more water than all the oceans of the Earth, like maybe 5 or 10 times more water than we have on Earth. And of course, there's Mars, we think might have been warm and wet in the past. So lots of places, even in our own solar system, where maybe life could have formed or could be today or in the past, right, that we're looking for. There's also a little bit of life as we don't know it that we're starting to think about. This is a picture of Titan, the biggest moon of Saturn, in the infrared, and you can see some liquid ethane, methane, like really, really cold alcohols kind of thing, lakes that are on the surface of that moon. And so there are thoughts on other non-water-based life options, right? So maybe ethane is a solvent instead of water, with carbon-based organics. So Titan. Of course, now that you guys have probably seen a lot of movies, AI, artificial intelligence, robotics, it's possible that things we could make self-replicating machines. Software could be examples of life in that very general definition that Stephen Hawking gave. And maybe there are other chemical options like boron, silicon, and whatever, but those have a lot of challenges. So we're still trying to figure out if that's possible. Anyway, there's a lot of options, right, for life. And so when we go back to this kind of fun question of like, well, given how giant the universe is and how many planets there are, where is everybody? There's some stuff that we need to think about, right? One is, simple life. I think a lot of people in the science community would be surprised if in the next 50 to 100 years we don't find this, right? It's given how tough we think life is, we think it's pretty likely that there's simple single cell life other places, probably lots of places in the universe. We haven't detected it yet, but that's kind of the lean right now. Intelligent life is maybe a harder question, and I'll talk about that in a little bit more detail. So one of the kind of interesting thought experiments to do, and this is the source of the quote. So I think I gave you guys a quote from Enrico Fermi, where he came up with this, at lunch in the 50s, I think at Los Alamos National Lab or somewhere else, came up with a quote like, "Where is everybody?" Right? And I think he was doing this thought experiment in his head, roughly. So our galaxy, the Milky Way, is about 100,000 light years across. Here we are, the sun. This kind of shows where we are. And if you just kind of think about, hey, once you get an advanced civilization, and even if you can only travel 1% of the speed of light, which is way faster than we can go today, but imagine 100, 200, 300 years from now, that we can go that fast. If you give yourself that speed, allow yourself 500 years to colonize a new star system, and assume that you take a stop every 10 light years, it would take you a long time, 12 million years, right, to kind of colonize the entire galaxy. But the galaxy, the Milky Way, is about 12 billion years old, right? So that 12 million years is only 0.1% of the age of the Milky Way. So again, this is back to the, where is everybody, right? So one thing to think about is well, where is everybody, understanding what we think maybe the phases of evolution and thinking about how likely intelligent life might be, right? It makes sense to kind of take a step back and think about, evolution and its different steps. And so far, for most of Earth's history, we've only been dealing with kind of DNA, like internal transmission of information via genes, right? So evolution is kind of only enabled via genetics for most of life on Earth, and that's been going on for about 4 billion years now. The Earth is about 4.5 billion years, right? So most of the time, it's been that mode. Once humans and actually some mammals have developed language, and of course for us humans, we have books, other media. Now you have a different way to transmit information. It's not just genes, but you can talk to each other and pass on oral tradition. So humans, as well as many marine mammals, so orcas, other mammals in the ocean, whales, actually have culture, and they pass on, we think, kind of, teachings and things like that. So they have a version of culture. And of course, humans, we've been doing that for a long time, about 200,000 years. And the last 10,000 years, since the beginning of civilization, we have writing. So of course, now we can write things down, and it means we can learn a lot faster and adapt even faster than before. And looking forward, maybe there's this evolution, self-designed evolution, genetic engineering, artificial intelligence. Who knows, if that's going to work, and where that might lead, and if it's even a good idea. But those are probably the different stages of evolution that we need to think about when we think about the likelihood of life in the universe. Another thing we need to think about, and is when we're trying to think about why haven't we detected life, right? And whether or not life will make it long term. Intelligent life will make it long term on a planet. I'm going to go through this. Different people have come up with different scales of civilizations. Most of these, I would say, are kind of like male-dominated, kind of power-dominated ways of thinking about it. Kardashev, a Russian guy, thought about energy scales, harnessing the energy of the home planet. Civilization scales 1, 2, 3. If you've heard of Kardashev civilization scales. Zubrin came up with a real estate version, spreading across your home planet, colonizing the solar system, going beyond. There's a dimension, ability to manipulate time and space kind of version. And so the red boxes kind of indicate where I think we are. I think there's a missing one, and you guys might relate to this. I don't think anybody's come up with this yet. I would call it kind of the Enlightenment scale, and it's probably important if you want to keep yourself from wiping yourself out, right? So where are you on the compassion enlightenment scale? Are you just love your tribe, love your nation or broader belief group, maybe love everything on the planet and all the sentient things connect with the universe? I would say right now we're only in the love your country for the most part, right? There are some people, maybe this group included, that think of citizens of the planet, kind of scale, but we probably need to advance along this scale, I would say, to keep ourselves from wiping each other out. So we'll talk about that right now. So I think I'm running a little bit out of time. I'm going to skip this. So possible reasons for lack of detection, right? So either intelligent life is crazy rare, or it's short-lived, right? So maybe Genesis is really, 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 really rare, and we're kind of wrong in our estimate that if you just give life a little, like chemistry, a little time, it'll form life in the right spot. Maybe the universe is just a nasty place, right? There's unstable stars, gamma ray bursts, all kinds of things can just wipe out life or push the reset button very often. And that maybe allows single cell life to form, but maybe not complex life in certain parts of the universe. And again, the point I was just trying to make, maybe compassion doesn't keep up with technology and intelligent life ends up pressing its own reset button before it gets too far as like colonizing the galaxy. So hopefully, we need to learn how to not do that. Another thing of like why maybe we're not finding anybody is space is huge, and maybe you can't cheat the speed of light, right? So space is just unbelievably gigantic. We don't have time to talk about that, but it might just take a long time to get anywhere. And so by the time, having a conversation, trying to make conversations for organic life is just not viable. And then machine life, if it happens, just doesn't want to waste time talking to us, right? Because it takes forever to talk and we don't live long enough. And then the other thing is maybe detection is hard, right? So maybe they're out there and we just can't find them. So advanced civilizations, even like us, we made a lot of radio noise when we first became technological about 100 years ago, but now most of it's like internet and over fiber and things like that. And so we're much quieter as a species on Earth. And maybe large scale. So people talk about maybe how come we haven't found like giant astro engineering things with our telescopes? And so maybe you just don't need that. Like as life gets more intelligent and advances, maybe they don't need to build giant things, right? They find compact kind of ways to make power sources and things like that. Anyway, and then maybe also advanced civilizations just find it very easy to hide from primitives like us, right? So those could all be different reasons of why we don't, we haven't detected anybody yet, and maybe they just don't want to, right? Prime directive, if you guys remember Star Trek, right? There's a prime directive like motive. It's like, hey, don't make contact with the primitives because you're going to mess them up because they're not ready for it. So anyway, fun things to think about as far as, the odds of life in the universe, maybe why we haven't found it yet, what our future might look like. I know I'm really short on time here, so that's kind of the main stuff that I had. I had one more like closing video, but if you guys have questions or want to talk about anything, happy to chat.
Hi, I have a question. It sounds kind of bizarre. Last night, I had my phone in my pocket, and I didn't realize it. And I was going around the house to shut down the lights, and the sound kept coming through. And it was like, I want to say, a little ghosty sounding, like, ooh, okay? And finally I realized it was my phone in my pocket, and when I pulled it up, it was from NASA. I don't know how I got on it. And it was showing that the stars makes a sound. Is this true?
Huh, that's interesting. So maybe you like pocket dialed some web link or something. So I think, stars definitely vibrate, right?
Okay.
A lot. They vibrate at different frequencies. And some people, I think some scientists have taken like stellar vibrations and maybe converted them to audio so that we can kind of hear them and maybe try to, as a way of like analyzing the vibration patterns. So sometimes we do that, even though it's at a different frequency that you literally couldn't hear, but then we turn these vibrations into our, like the range that our ears can hear to help us use our ears for pattern recognition.
Well, thank you very much.
Thanks, that was really interesting. Do you have your own view of the cause of the Big Bang? That is, what caused the singularity? And there's this philosophical idea that there was no time before the Big Bang, so don't think about it. But that's never been very satisfying to me. What do you think is the explanation for that massive concentration of energy and matter?
We have no idea. The honest answer is we have no idea, right? And so I think that remains a huge mystery. And I think it's why I'm not personally religious. I am agnostic, but I think there are so many mysteries and things we don't understand about the universe that it's perfectly rational to be able to like have some kind of like, I don't know, like just awe and belief in a greater thing. Because I mean, like, you can't prove that there was or wasn't something starting the Big Bang, right? Or if it was just physics-based, like, who knows, right? And even if it's physics-based, who made, like, how did the rules come up, right? So we just don't know, and we're still trying to figure that out.
Thank you very much. Very, very interesting. I have two questions. The first one, on one of your slides, you say that civilizations or go silent after a period of time. And you used the Earths in the last 100 years. What exactly did you mean by that?
So I meant from a, like, pretend you have a radio receiver at Jupiter and you're listening for Earth, right? You're just listening, or even, you know, somewhere else in the solar system, you're pointing your antenna at Earth and you're listening to what's the noise coming off our planet. So when we first created radio and TV, we had these, you know, the technology wasn't very good. We had really, really powerful transmitters, and the antennas were omnidirectional antennas. So we were just spewing radio signals, you know, everywhere, including into space, when we were just trying to transmit radio, like, you know, to the across the city, or, you know, TV across. And so since then, we've gotten a lot better. Like, and by the way, at the beginning of the information age, right, like radio, TV, broadcast was the only mechanism, right? Giant transmitters, big power, broadcasting signals out. And now, how many of us still pick up TV from, like, broadcast, right? Most of it's internet, you know, fiber wires, etc. And so the amount of just, like, noise, like, power leaking from our planet has gone down, right? So we are becoming a quieter, even though we're sharing more and more information, we're, like, much more efficient at how we do it. And so that's what I meant by becoming quiet, right? So because the reason it's relevant is right now the main search for extraterrestrial intelligence is listening for radio signals. Like, we point giant antennas at other stars and we see if they're transmitting in the radio, like some radio frequency range. And we haven't detected anything. And so if you imagine that the time when a civilization might be loud is very short relative to the age of that civilization, right? That's why it's important. Does that make sense?
Yeah, it does. Thank you very much. I mean, I was just thinking that we've become a much noisier place with all of our electronics, but as you point out, it's not as intense. It's just more ubiquitous.
There's definitely, yeah, I think sure, at low power levels is way more,
right.
But at high power levels is way less.
The other question I got for you, because you read different views and different opinions on it, is the universe expanding or contracting?
Expanding. And it's actually one of the, like, freaky things. The rate at which the universe is expanding is accelerating, which I think 30 years ago nobody was expecting. But as we were looking at, you know, these different, like, mile markers, there's natural mile markers in space that we can use to figure out how fast everything's going. And the further you look back in time in the universe, the more we can tell that the rate of expansion of the universe is increasing. And that's why, like, there's this whole theory of dark energy. And so dark energy is just this thing that we made up because we have no idea. Like, we're like, hey, something has to be powering the universe's expansion. We're going to call that dark energy. And it's just a huge mystery, like, why that's happening.
But my question is, related to Mars, that would seem to be the most likely place that we would find life. But also they're sending a mission to Titan, the Dragonfly. Yeah, and there's other places. What do you think would be the most likely place that we would find some evidence of life?
If you gave me infinite money today and said, go find life, I would send a probe into the oceans of Europa, this moon of this kind of cracked ice shell moon of Jupiter, because we think there's energy there, like, because of tidal forces. That probably has hydrothermal vents like Earth does. The problem with trying to get into the ocean of Europa is there's a 10-kilometer, like 6-mile thick minimum ice crust. And so before you can stick a submarine in there, you got to get through 6 miles of ice. So that's why you need a lot of money, and we don't we don't have that yet. So we were sending an orbiter. We actually launched the Europa Clipper, which will be orbiting the Jupiter system and looking at Europa and measuring like how thick the ice is, at more precisely. It's going to get there in 2030. Once we do that recon, that more in-depth recon of Europa, then hopefully we can plan a lander or a subsurface mission. But that's going to be, maybe my kids will be working on that, or your grandkids or something. So anyway, that's probably the most likely place, I would say. But Mars, yeah, Mars is the easiest place in the solar system to get to. And now, based on the 60 years plus of exploration on the surface and orbiting Mars that we've done, we have really, really strong evidence that says Mars, near the beginning of the solar system, the solar system is 4.5 billion years old. Probably the first few 100 million years of its life was warm and wet like Earth. And so we think there's a chance, there's definitely places on Mars where there was just flowing water, neutral pH water. And if you brought bacteria from Earth there, to that condition past Mars, they would be happy making a living. So we're hoping to find evidence of fossil ancient life on Mars, and maybe deep underground, just like on Earth. If you dig a 5 kilometer or like a 3-4 mile deep hole on Mars, you probably would find, maybe you'll find bacteria, still making a living down there, but we don't know yet. And that's also hard to do, right?
Thank you.
So you talked about in one of your slides an omega stage, which was like a last stage. Is that a theoretical thing?
Yeah. So this is So these civilization scales. Science fiction authors, thinkers, cosmologists just like to think about, like, imagine how advanced you could be in the future, given what we know about physics, and then just like put a scale to from where we are today till there, right? And like calling those different things, right? And so this Barrow scale of dimensions and manipulation, his definition of omega was, a civilization that could manipulate the fabric of space and time, and so it could go forward in time, backward in time, use effectively like warp drive, like jump around in space, right? We are definitely nowhere near that. We are probably, I have no idea if that's even possible. Might be impossible, but it's just a theoretical construct, right?
Let's go back to the Big Bang here for a minute. If we assume that was a natural phenomenon of some sort that we don't understand, spontaneous creation of subatomic particles that basically ended up with a singularity, it would seem to me very unlikely that it was a one-time deal. Therefore, our universe is not the only universe. Isn't that the logical conclusion?
Yeah, and I think that's also one of the theories. So we have this ever-expanding universe. It turns out, like, we also, even in the current state of the universe, there's evidence that there is just a vacuum energy. There's some kind of like bubbling of like space that has energy in it that's very faint, right? And so I think one of the theories, I'm not a cosmologist, so you might know more about this than me, is like, if you make space empty enough, like once the universe expands enough, like maybe it just pops another one, right? And again, maybe, right? And so sure, you might have different ones kind of just popping out of the vacuum for who knows what reason. And then even if once you've had one, if it just dissipates, right, over billions and trillions of years, that maybe something else just pops up in its place, right? So, I mean, like, it's hard to wrap your head around like why and what's going on there. I don't think we know that, what's going on there yet.
Recently, I guess the last 10 or so years, more people have been coming out that have actual experience and high ranks in the military, saying that these UFO things have been covered and now they're talking about it. What is your take on all of that?
Yeah, so this slide, I ended up skipping this slide, but maybe it's worth talking about a little bit. Like, so this is, what can we kind of factually say about what we've seen or not as far as making any kind of contact, right? So there's three buckets here, right? Radio waves or light signals from extraterrestrials. You know, we've had some hints of like maybe some exciting things, but nothing that was repeatable and verifiable. So we have not had any detection yet of radio waves or light signals from any intelligent life in the universe, as far as we can tell. We have not seen any obvious like giant astro engineering projects, right? So Dyson spheres, Dyson rings, you know, it's like imagine a civilization that like mines all of its asteroids and builds some huge, you know, structure in its solar system. No evidence of any of that, of any of the star systems we looked at. But we've just barely started looking for both of these top two items, right? And I think you're getting at this local contact question, right? And I would say it's not clear, right? I mean, so maybe, probably not. But really, I mean, so I think it's healthy to be both open-minded skeptically and open-minded that maybe there's something happening. Again, because when you look at the size of the universe and like how many, like it wouldn't be a surprise, right, if there was some intelligent things around. But I think we can say there's definitely nothing in a deliberate, undeniable, in-your-face, land on the White House lawn or the lawn of the UN and like make your presence known in a hugely obvious way, right? Like that has not happened. Now, are there bored teenagers, right? Or like, you know, whatever, like some kind of, are there maybe things that are flying around just trying to check us out? Maybe. We have no idea. And again, I think we don't know, right? So I think it's important. There is a stigma associated for a long time, right? I would say kind of like almost an anti-science stigma of like just ridiculing anybody who even brought it up, right? And I think if you're open-minded and curious, like you should think about it and investigate and like take it seriously. And I think we're just beginning to do that, thankfully. But I don't think we're at the point where we can say that any contact.
If we depersonalize the term chaos, how does it play out in a universe that is supposedly orderly?
Yeah, so this is kind of like a little bit of physics 101, but one of the things you learn about in physics and engineering is there's the second law of thermodynamics, which says overall for any reaction or process to move forward, the net order of the universe has to decrease. Okay? Like, but you can draw a big circle, so that's like the biggest picture law, right? However, you can locally, right, within the system, as long as the net order is decreasing, you can still organize locally, right, and create more order. So like gravity, I would say, is a big ordering thing in the universe, right? It creates a lot of order. And, you know, but dark energy, these other things that are kind of pushing the universe apart, you know, there's other stuff that, and just, I mean, you can tell, like, when you do anything, like, it's easier to destroy things than to put them together, right? Like, things want to fall apart, and you need to put energy in to kind of keep them together, right? So gravity is one of those sources that, like, puts energy in to, you know, create order. Life takes energy from the outside and creates order locally within it, right? It kind of organizes its cells, it organizes a body or whatever, organizes a planet. And so anyway, so I don't know if that answered your question, but that's, you know, but if you zoom out, the net disorder has to increase over time, but it doesn't mean that you can increase, that you can't increase the order. And I would say even if you take, if Earth is typical, right? I would say life creates more and more and more order over time, right? Like the complexity of life on this planet has been kind of monotonically increasing for 3.5+ billion years, right? So anyway, so there's kind of competing things there, right? I don't know if that helped.
Any more? No?